everyone. Good afternoon. Can you hear me? Okay, thank you. So let's begin again. So this time we will look into how can we combine the good things from large language models and GAN together to get higher accuracy for our information extraction task. So there is this paper called GAN-IE, a Generative Adversarial Neural Network for Information Extraction with Limited Annotated Data. So here we are going to demonstrate this in this case study that if you have very limited amount of data, you can utilize GAN to get quite good accuracy. The paper, so the if you are using the paper, this is the citation. You can make the citation, and the paper is available. Let me show you. So share. So I think the paper is available through Qt ePrint. I will share the paper. So this is the paper. Okay. From Qt ePrint, you can get the paper. So I'm going to share the Qt ePrint link. You can get the paper from there. Okay, now let's see what is the idea here. So you can see you have the BART model, right? And then using BART model, you can fine tune it, and then obviously that can give you good accuracy. The problem is if you don't have enough training data, like enough label data, then it becomes difficult to fine tune the model, and then your accuracy might not be quite good. So in that case, we can utilize GAN to learn from the unlabeled data. So GAN can help you, as I explained earlier, GAN can help you to learn from unlabeled data, the manifold or the overall distribution of the data in the domain. And then you can utilize that learned distribution or like variation of patterns that are there. And then you can utilize that one to improve your accuracy. So how, okay, so there could be some questions like about, one question was, can we use GAN for information extraction? Yes, we are going to use the GAN for information extraction, but not the way you are thinking that one could be like in a pure generative way, how language model works, right? So in the language model, you ask to generate the text and then it generates. Technically, it is possible. You can set the GAN in that setting because it is a generative model. Obviously, it can generate, as it can generate images, it can generate sentences as well. That is possible. The problem is GAN is little bit, not little bit, in a way, a bit slow compared with plain BART model, right? Because you have like two models that compete each other, learn from each other, and then that a study will show that running a GAN model is equivalent to running 4 models together, right? So that means it is computationally it is quite expensive. On the other hand, generative models, if you are using like decoder model, like how GPT works, right? So you can both GAN, and the advantage of GAN is that it can learn from unlabeled data, but also the generative model, GPT models, generative language models, that can learn from unlabeled data as well. So in the language model, given a sentence, so in the sentence, you know which word appear after which one, right? So you know the sequence. So and then you send it to the language model, it will simply try to predict the next word again and again, right? Through the iteration, then it learns from the unlabeled data. You don't need to label that. And then you can you utilize the unlabeled data in GAN as well. But because the generative or GPT based language model is much faster than GAN, so obviously you're going to use a model that is computationally less expensive. That is one thing. Another thing is because the GAN is versatile. It is not dedicated for like sequence generation. Obviously, you can replace the inside layers with say transformer based model, and then you can generate the sequence possible. Again, if you are utilizing the transformer inside the GAN, that becomes expensive compared with if you are utilizing only one transformer model, like the decoder part of the model, GPT based model, right? So that's why when you compare the computational cost, then for text generation, people use GPT-based model or large language model instead of using GAN. So that is the reason. But now, why GAN? The GAN is if you need for a specific area, you need to fine tune your say language model or any other model that has very limited amount of annotated data. Then GAN can help you. Okay, I'm coming here. Why can it? Yes. Okay, now let's see how it is going to work. Let me use the pointer option, the pen. Yeah. So what is happening? Let's explain this part first, right? So you have label data or unlabeled data that goes through the BERT. So BERT gives you a representation, but this representation can have any value, right? It can be 1.3 or 0.3 or whatever, right? It is not bounded. And we from last yesterday, we know that to make GAN model more stable, we need to do the normalization, like data normalization, so that the data is within the similar range that makes the GAN converse faster, right? So that's why we use a tanh function here, right? The purpose of tanh here is just to normalize the data, nothing else. Just to normalize the data, because tanh will squeeze the data between -1 to 1, so your data is normalized. So that's why we use tanh. You can argue why not sigmoid or some other thing. Technically, you can use that, but if you use tanh, you can see your data can be from -1 to 1. That gives a little bit like more space to represent the data. But I think you can test with and sigmoid to see if it gives you better result. Okay, so now after tanh, you have the normalized representation of your document or text, right? So now this text goes to the discriminator, right? So we know that the discriminator can tell you whether this one is real or fake. So this part tells in the discriminator tells you whether it is real or fake. So based on your real or fake, you can update your discriminator. So this one is sending the real data, and as I explained yesterday, you have a switch here that can switch between real and fake data. So in one instance goes the real data, maybe another instance goes the fake data, and so on. For the generator part, you sample from the noise, and then you generate the data, and then your discriminator tells you whether it is real or fake. Based on that, you update the discriminator, and also you can update the generator, right? The same setting. So this part is quite common. Now, through this training process, you can see that your discriminator will eventually know how your real data looks like. Uh, all the variations in the patterns it will see to distinguish between real and fake data. So the variation is learned, and that is coming from both labeled and unlabeled data. So you have lots of unlabeled data. From that, you can understand how different patterns look like. and that helps the discriminator know all the patterns. Now for the label data part, so the label data part comes through the part, gets the representation, and then beside the telling that whether it is real or fake, it gives you another loss or another prediction. It gives you the start position of your answer and the end position of your answer. Okay? So these two position it will generate. So now if you use this to against your ground truth answer start and end position, then you can calculate a loss based on the prediction and the ground truth that you can utilize to improve your classification activity in the discriminator. So the discriminator works or gives you two tasks. One is telling you the real or fake, and another part is giving you the start and end position of your question, sorry, of your answer to the question, right? Now, one interesting thing you need to see here is that this is not a generative model, right? You are telling the start and end position. So it is an extractive model. You just indicate or refer answer to the text or the input text where the answer is appearing, right? It's start and end position. You are not generating anything. So it is immune to hallucination and those kind of things. It will not generate new data, so no hallucination. Yes, it can make mistake, but whatever it gives you, it will coming from the context or from the text, right? It is not something completely made up. So that is like one big advantage if you use extractive information extraction or question answer system, right? So now you can see how it helps you to get the better representation and prediction accuracy through GAN model. So what are the advantages if you use GAN IE, right? GAN-based information extraction. So it gives you improved generalization because now you're learning from both labeled and unlabeled data. The data distribution your model sees the much more varieties, so it knows overall data distribution. So that is one thing, and as a consequence, actually, you can handle the data scarcity. That means if you have a limited amount of label data, you can utilize the GAN settings that can help you to overcome the data scarcity. Obviously, it gives you the better feature representation because you are now learning from various samples, various unlabeled samples. So all the variations and how to more more optimally represent your data. And the thing you can see, all the knowledge you have in the part that is already there, and in addition to that, you learn from your specific domain. So that makes the overall model better. Obviously, because now you learn from the unlabeled data, so you have more data, so you have less risk of overfitting. So that helps you to reduce the overfitting problem. And also, yeah, leveraging unlabeled data. I already told that. So now you can see we have that adversarial training phase where you train your model with labeled and unlabeled data, right? And then progressively through different many iterations, you train your discriminator in like more confident discriminator or more reliable discriminator you'll get. I'm not going through the details of the mathematical things here, uh, but the things that actually we already discussed those things yesterday. So I hope you understand what is going on here. So like it has unlabeled laws and label laws, right? So just I'm going to give a quick overview what is happening here. So for this part, label part, you have like start and end position, right? So this part will help only the classification purpose. So this loss will go only to the discriminator, and the real and fake part, that also has another loss that will go to the discriminator as well, right? So you have now the three parts in a way. So to say whether it is real or fake, if real one, and if so for the real data you get one loss, for the fake data another loss, that two thing, and then also for the classification. So these three components will update your discriminator model. On the other hand, your generator model will get only one loss, which is if the fake data is identified as fake, during that time you will penalize the generator, right? So that's how you train your GAN model in this setting. So now, once this training is done, you can see if you need a generative model, where say you need to generate faces or new data. Usually people use this generator, right? They take this generator and discard the discriminator, because they just need to generate new data. But in our case, we don't want to generate new data. We want to predict their starting and end position. So what we will do is we will discard the generator. We will only take the discriminator, and also we don't need this part during the inferencing or during the testing, right? When we deploy the model. So we don't need this part. We take the discriminator, remove the generator, and also in the discriminator, we don't care about this part, real or fake part, because all the training is done. So in the prediction, we simply predict the start and end position of our answer, right? So now through that, you can say you have this loss function, real and fake, and then you have you have adversarial and unsupervised loss. So you combine them together. So you have that part is done. Like, so this is real and fake part, and then you have the start and end position loss, like this one. Now, after all the training is done, uh, uh, what happens is sometimes uh, obviously it is not going to be 100% perfect. So sometimes the answer might be wrong, or maybe partially wrong, and so we do some post processing, right? So in the post processing, what we do is, because it is telling you the start and end position, so you have the context. Say this is your sentence or a paragraph, that is the context, and then the answer should be within this start and end position. Like, say the context starts at, say, position 12, and then ends at, say, 100, right? So your answer must lie between these two boundary. If you see that your model predicts a start position which is before the context, if it is before the context or after the context, for the start or end position. If it is beyond that, then obviously your model is making some mistake, right? So what we do is, actually, instead of predicting one start and end position, we predict, say, 10 start and end position, and then we check if they meet this condition, right? Some of them will meet, some of them will not meet. So we can say, then we end up with 5 predictions that looks like meets this condition, that start position and end position should be within the context. And for this remaining five instance, like prediction, then we check we know that the start position must be smaller than the end position, right? Otherwise it is a mistake. So we check for that constraint again, and then that may be lead us to remaining 3 answer, 3 prediction, 3 or 2 prediction, right? And then for those ones we consider the confidence, and like prediction confidence, like what is the probability, this is the start position, what is the probability, this is the end position, right? So we take the most confident one, and then that one we take as the answer. So that is like post processing part. Yeah, and then yeah, we do the inferencing. So here we discuss that part, that we are doing, how we do the inferencing, and then see, we take the topmost promising ones, and then we do the post processing over that and get the answer. So for this one, we used a small data set to see how it works. So you can see here, you can see how the source of the data, then also the distribution of different questions, how many samples for different category. And you can see we have 2,500 samples for, I think, um, yeah, per category, 2000 to 2005 samples here. 4,000 for, I think, unlabeled samples and 2,500 for label samples. And then we'll see if we change this number of label samples, how the accuracy varies. So here you can see the accuracy, F1 score. First one shows the F1 score compared against the baseline model. So we used several baseline models. This one is our model, Gen IE. And then we compared this one against Roberta, BART, Distilbart, Albert, BiLSTM, and those things, right? And then you can see in the x-axis, this is the portion of data we use to train, like portion of label data that we use to train our model. And you can see our model is this one, right? This curve is our model. And you can see from the very beginning, even with 1%, 5%, 10, 8%, 10%, you can see from the big, with just around 15%, or if you go the peak, just using 25% of data, we get really good accuracy compared with all the other models. And if you add more data, obviously this one goes like not too significant change, and other models goes higher, a little bit higher, but still our model is better than other models, right, here as well. But the significant difference is when you have a small number of label data. Right? So this shows that our model can learn from a very small amount of label data. Right? If you have data scarcity, this kind of settings can help you. And here you can see the recall and precision. For recall and precision as well, we are getting significantly better, just about 25% of the data. If you have only 25% of data, we can get the similar accuracy as 100% of the data. So which is very good for if you have very limited amount of data. Here we are showing the F1 score for different questions. So you have different questions, and what is the accuracy F1 score for all these questions. And you can see that the accuracy is quite good actually, right? Here it is more than 90% accuracy, which is really good. So recall is 85%, and then okay. For some of them, see, for some of the questions, the accuracy is 99%. For some of them, it is not that high, maybe 85% or 84%, right? 84%, 88%, so on. So the reason is actually you don't have, you have different questions are have different level of complexity, and also the data distribution for different questions are not uniform. So for some cases, maybe you have very small amount of data, and some cases you have a little bit more data. Okay, why recall and precision? The why not accuracy? Sometimes accuracy can be misleading. Yesterday we discussed that you need both recall and precision. So if you want to capture all the positive instances, right, you can you try to get higher recall. On the other hand, if you want all the positive prediction be accurate, you want higher precision. But if you increase one, another one can go low. So if you can increase both of them, that is very good. So that is measured through F1 score, right? Now, why not accuracy? The accuracy sometimes can be misleading. Say you have a data set of fraudulent fraudulent transaction, right? So in the transaction, you will see 99% of your data is legitimate transaction, maybe just 1%, not just 1%, maybe just 0.1% of the data is fraudulent or fraud data, fraud transaction, right? Now, if you design, if you simply write a printf, right, that will always say that your transaction is valid. So you can say, you can see that you are all 99.99% correct always, right? Still, your model is not doing anything. You are simply saying everything is valid. So in those cases, even though your model is giving you 99.99% accuracy, your model is doing nothing, right? So how do you capture those things? So to capture those things, you need to analyze your recall and precision. That tells you whether, so for example, recall will tell you whether it is detecting any of the fraudulent transaction or not, right? So without using that, you don't know if you could identify any of the fraud transaction, right? So that's why you need to analyze, use those things. Okay. So remarks from GAN-AI is that you can see it is very effective in the scenario where you have limited label data, right? In that case, you can use GAN-AI. So the future work would be, so in the GAN-AI architecture, we in the future we are planning to use transformer model to see how that can improve the accuracy. And also we tested with this one only with Department of Resources, like geological data. We are planning to use it in other domains to see if it can still give you this kind of accuracy. So future trends in AI and information extraction would be seeding your data annotation. So because it can extract information that can help you to train different kinds of models, and then that would be very helpful to, like, now there are concepts like informed neural network and other things where adding extra information can increase the accuracy of your model, right? So information extraction can give you that extra information that can improve the accuracy in prediction. Another thing we saw that it can help you to understand the context better, right? If you give more information about a context, then your model will understand the context better, and then it will give you reliable prediction. Another thing is currently people are moving towards multimodal data processing. Now people use text, image, and image, audio, and many other things. So for example, if you are in a medical domain, you want to see the doctor's report, the x-ray report, the blood test, and so on, combine them together to make a better prediction about the disease and recovery. So that's why you will see in the applications that now there is a significant trend towards using multimodal data instead of using a single modality. Okay. Another thing, as I said yesterday, explainable AI would be a very significant research area for at least next several years. The reason is we can see that these generative models or many deep learning models, they are very accurate. The problem is we don't know why they are making that prediction, right? So to use them in critical situation, for example, in healthcare or self-driving car or like defense, those kind of situation, you want to know why it is making that prediction or why it is making that decision. If you don't know, then you don't know what will happen in some uncertain scenario, right? Maybe it will make some mistakes, and then everything will be in disarray. So that's why people are now working towards explainable AI. Another trend would be utilizing mechanics or quantum computation in the generative AI, because generative AI needs huge amount of computational power, and you can see that the generative AI mechanism of training generative AI is stochastic, so there is randomness, and quantum mechanics is also based on that stochastic kind of process. So one thing is quantum mechanics or quantum computation can gives you a huge amount of computational power. So that will help to boost the generative AI models better. And also, it's the stochasticness in the quantum computation aligns with the stochasticness in the generative AI. So there will be a like significant trends towards utilizing quantum computation for generative AI. So what could be some of the potential research area? Obviously, generative AI and information extraction, they can help you to analyze unstructured data. Particularly, you can use them for name entity recognition. Large language model can help you to like interact in a more user-friendly way. In the robotic process automation. So that means you will see that people are using generative and those extractive AI models for information extraction that can help them for data entry task. Multimedia, obviously, it will be utilized for multimedia scenario, image, text, video, those kind of things. It can improve data quality in the annotation, right? It can extract and give you the explanation of extraction. That's how you can improve the data quality. Explainability and transparency, obviously, that will be important. Can we use it for part of the speech tagger for code mistakes? Yes, that is possible. But as far I understand, at least for English language, part of speech tagging is quite stable. There are many models that can give you very high accuracy for part of speech tagging. So part of the speech tagging for English language is considered a solved problem. So, but if you are considering for other languages, especially the language that are not, that do not have this kind of big models, then in that scenario, yes, you can use this for parcel speech tagging. So this is like a theoretical analysis of the case study and then other things. As I mentioned yesterday, this is my contact information. You can connect with me through LinkedIn. You can see my website, and this is my email address. But you can understand that um, like sometimes I cannot reply the email, busy with other things, but a good way is to connect through LinkedIn, so you can get my update and then like give a message to me. That's good. Yeah. So let's move to the coding part. So as I promised, today I would like to run the model for both CPU and GPU to make sure that it is running for both cases. Okay. Um, yeah, mention this one. So I will start with the DUR model, this one, and this one. So similar to yesterday, first I will explain what is going on there, and after explanation, we will start running the code. Right? So this during running the code, you can ask me questions. If you have any problem, I can try to help you to run the model. Okay, so this one we will do it through Hugging Face. So the base, okay, this one is let me see if I have yeah, so you can see this one is for question answer system, the large language model or BART based information extraction part. So you give the question and then the context, and you get the answer at start and end position of the answer. So that model we are now explaining. For that one, Uh, so first I'm checking here if the CUDA is available. So now today I actually made it more dynamic. So you can run this code on CPU or GPU, doesn't matter. It will check first if you have GPU or not. If you have the GPU, it will use the GPU. If you don't have, it will use the CPU. So it will run both on CPU and GPU. You don't need to change anything. It should work. Okay, now you can see here, first we are checking the CUDA. If the CUDA is available, we will use that. So here we decide the device. You can see if the CUDA is available, we will use the CUDA. Otherwise, we will use CPU, right? So this one decides which one to use. And then for the different set of resources, we have this training and testing data. For the demonstration purpose, I will use only 50 samples. So you understand that if I train it for only 50 samples, the accuracy might not be very good, might not be good, or it will be mostly random. But if you use the full data set, obviously you will get a good accuracy. So let's see how it looks like. As I said, I cannot share the data, but I can show you how it looks like. Uh, so this is the test, this is the train, right? I can open with here in here, right? So you can see we have the ID, right? So we have the ID of the document and the title of the document, and then we have the context. Answer is 215. Answer starts at this point and ends at this point, right? So that is what we have. So we have many of these samples. This is here we have only 50 samples, but in the full version we have, like, as I explained, several thousand. I have the full version as well, but as I said, we can't share that data. Okay, now so here you can see this is our train data and test data, and then we have a data loader. The data loader reads the JSON file, and then in the data file we have the training part and the validation part. So the train file, this file location, data in this location, I'm going to use that one for training purpose, and the test file, this location, data in this location, I'm going to use it for validation purpose, right? And then after reading, you can see this is the description of the data. So this is your training data part, this is your validation data part. In the training data, you have 4,925 rows and 1,200. So I think this one, yeah. Okay, so here we are showing one example how it looks like. So this is like ID, as I explained, ID, title, context, question, and answer. Yes, along with the text, we need to give the question answer simultaneously. Yes. Can we use GAN for fact checking? Uh, for the fact checking, technically true, but the problem is now if the fake news is coming from another generative model, sometimes it becomes tricky to identify that one, because um, usually in previous times, people used this kind of models to find the patterns of fake news. And then now the fake news people, they know how to utilize generative models to generate the fake news. So it becomes a little bit tricky to check, to detect the fake news. The first answer is yes, you can use scan for fake news checking, true, but the accuracy might not be quite high if you do not consider other things. For example, the context, the situation, and some other things. Like, so people use other things along with GAN to like increase the accuracy. Using simply GAN might not give you high accuracy because of the nature of the fake news. Okay, now you can see the data, and then we defined a, sorry. So we defined a tokenizer. We need a tokenizer to tokenize our data. So this is the tokenizer, and we are going to use DistilBart base uncased. This one is very lightweight, so you can run it with the small GPU or on CPU. But if you have like enough GPU, you can use the bigger version. Then in the pre-processing, right? So in the pre-processing part, you can see one example. That means this one is one example, right? This, where is it? Yeah, this is one example, right? So this is one example. So you have many examples. So you take examples, and then you do some pre-processing. For example, the question part, I'm just simply doing some very basic pre-processing here, just to demonstrate how to do the pre-processing. So it will strip the question. That means it will remove the extra space at the beginning and the end of the question, right? So that is what we are doing. And then we send it to the question, and then the context through a tokenizer, right? So the tokenizer will take the questions, the examples, that means the context, right? And then define the maximum length. What should be the length of the context? So 384 is the context. So if the context is smaller than that 384, it will pad the context, so add extra like 0 or extra token, like a padding token like PAD or something like that. And then it says truncation only second. That means it will truncate from the last part of the data. So if your context is bigger than 384, it will remove, like truncate some of the data points, some of the words or tokens, and that will be done from the end side. So return offset mapping true. So because our data is in the character representation, so the location that is start of the question, start of the answer and the end of the answer, that is in the character wise position, right? The index is character wise. So that means at which character the answer starts, and then at which character the answer is ends. So it is in character space. And then because when the model generates the answer, the model actually is based on tokens, not based on character, right? So it will generate the token base start and end position. So now you need a mapping mechanism that can map from characters to the token, and then back token to the character, right? So that's why this mapping, return mapping offset. So this will tell you the mapping between character and token. So this is your offset mapping, and the answer. So this is the answer part of your example. So you have that. So here we need to now know we have the answer position in character domain, right? Character space. Now we need to convert it in the token space. So we store that start position and end position of the answer in the token space. So offset mapping, for the offset mapping, you take the answer, right? And then you take the start position so which is like character label, end position at character label, and then so this one, instead of taking the end position, yeah, here it takes the start position and length of the answer, right? So which is same as taking the end position, same thing. You could take the end position, same thing. And then sequence IDs. So sequence IDs means you know that when you do the text modeling, each token is represented with one number, index number in the dictionary, right? Your list of tokens, right? So that one is the sequence ID. So that means each token is represented as one number, right? That is the thing. Okay, now find the start and end of the context, right? So the start and end position was in the character domain, character space. Now we send it to the token space, right? So you have sequence IDs, and then it indicates one means it is yeah, just this, give me a second. Find this. Okay, so we want to see where one is starting. So one indicates that maybe I just need to draw something that can help. Yeah, let me open the paint, right? So that can help you. So as I said, the model has two parts. Start the question part and the context part, right? And we said that we have a separator there, right? So this separator is in the input space. Now in the model space, actually model needs a mechanism to distinguish between which one is the question and which one is the context, right? So in the question part, so these are like tokens, right? These are your tokens, and in the answer in the context part, you have the tokens here, right? So what we do is for the question part, we indicate the question as using the zero, right? The zero. So these are the zeros. So this means these are questions, and then if it is one, these tokens are one. That means they are context, right? So we want to know where this starts. So how do we know that? If this index is one, that means or one. So whenever we start from seeing 000, whenever we find the one, that means it is the context. And then until it finds one, we'll continue. And then if there is no one, no more one. So if the zero start or something else, then we stop here, right? So we know the start and end position of the context. So here, that's why you can see we loop through here and try to see if that is one or not. If it is not one, we continue. Whenever we find one, that means we got the start position of the context. And then we need to find the end position of the context, right? So for the end position, what we do, we continue until it is one. Whenever it is not one, we end there. So that indicates that we have passed the context, and then we subtract one from that index. That will give you the end position of the context. Got it? Someone say not equal to one, I think. So now I think you understand that why it is equal to one. One means it is actually in a way indication of like which one is the question part, which one is the answer part. So answer part is one. Sorry, the context part is one, and then answer part is zero. That's how you know. That's why it is one. Okay, so you have the start and end position of your context. And then now you try to map that into offset. So you can see the offset. If you send this start and end position through the offset, so if you send it through the offset, you will get the corresponding token position. So you send it through this character position. This offset will give you the token position, corresponding token position. So that's what we are getting here. So start position in token space, end position in token space. So in the first in this condition, we are trying to see if the start and end position is within the limit, right? So that's what we are checking. If the start and end position of the character is beyond the index of the token space of the context, then we will assign that as 0. Otherwise, we will find out corresponding start and end position in the token domain or token space. See, here we are doing that thing. So you have the start position in token space and end position in token space. So you have done all this pre-processing here. Now you can see this is after that we have like many columns. Some of the like, for example, the title, the file reference, those things are not needed. So here I am deleting those extra columns. I'm just keeping the important ones only. Then here what you do is you take your data set and then you call this function map, and through this map function you provide this pre-processing function, right? Pre-processing function. So you provide this one, so that this map will apply this function for this whole data set. So we say we'll do the batching, we'll remove some of the columns, right? So that after that, after all these things, it will give you the tokenized representation of your data set. And then this one is so you could use other data loader, but other data loader, they have built-in pre-processing. But in our case, we have done the pre-processing, right? And the pre-processing is already done in this pre-processing function. So we don't need to do the pre-processing again. So we are going to use the default data collator. So default data collator will give you the batches from your dataset, but it will not apply any pre-processing, right? That's why we use the this one. So you define this one and then you pass through your data and then you will get the batch. So here we are explaining how the model will work, as I said. So you have the question part. Question and which one is the context. Okay, now after this we want to load our model. So there is if you go through auto model for question answering, so from this transformer we will use auto model for question answering, right? So that one, actually, if you use this one, that one has pre-trained Distilbert, right? So you load this pre-trained model Distilbert and then fine-tune that model with the label data set. So we load that one here. So this is your model. And after that, we define some training parameters. So we say where the output will be stored. So this is like during the training, there will be some trained model output and some other temporary files. All those things will be stored in this location. And then in the evaluation strategy, we'll use epoch instead of individual instance. So we'll train it through epoch. For each epoch, it will evaluate, and then learning rate. And so you can see that the learning rate is quite small, so that it doesn't oscillate too much. Per device train batch size. So batch size, you say 16. It is per device because in Hugging Face you can do the parallelization. So if you have multiple GPU, then you can do the parallelization. That's why it is per device. So this is like batch size is 16. So, and I'm saying train epoch 3. So train epoch 3 just for demonstration purpose. If you want to train, you may need to train it much maybe longer based on your data set and application. So for now we are going to use like epoch 3. weight decay. So this is related to how you will update your training, like learning rate. So related to that. So this is your settings, and then for the training you have two options. One is you can write your training code here, right? So I have that part here, so you can use this one. This is like a more manual way to train it, but if you are using Hugging Face, Hugging Face has its built-in trainer. Built-in trainer, if you use built-in trainer, it is very simple. So you in the trainer you provide the model, you provide the training settings, and then what you tell it what is your training data, what is your evaluation data or validation data, what is your tokenizer, and then data collector, like what kind of batching that you will use, right? So you provide all these things, and then it will train the model for you. And you can see after that, after defining these things, you simply call this function dot trainer dot train, so that will train for you. And you can see I have trained it, and then the training, you can see the training loss and validation loss. So the validation loss is going down, that means the model is working. Okay. And then if your training is done, so all the training is done, then you do the evaluation. So before you call the evaluation, you need to set it in evaluation mode, model.evaluation. The reason why you need to do is during training process, you update your model, right? So based on you, so your model for each forward pass, it will calculate the gradient, and then in the backward pass, it will update the gradient. So model will be trained during that time. That means model will learn from the data, model weights will be updated. But during evaluation, you don't want your model to get updated, right? So whatever you trained, you want it to stay there, and then and then evaluate the accuracy of the model. So that's why if you call evaluation dot eval function, then it will set the model in frozen mode. So your the weights in the model will not get updated. Okay, and then you can see what does the model look like. So this is the structure of the model. You have embeddings, and you have a number of linear layers, and so on, right? So you can see the details of the model here. We discussed yesterday how to check all these things, right? What does it means and so on. Okay, then you need to, so here we are checking what does the validation data looks like. You can do that. Okay, now after that, we tell the model to do the evaluation. So this is your validation set, validation.set format. So you convert your data into towers, what are the columns and so on. You give those things. Mm, um, so the validation loader. So now you use the data loader instead of default loader. You can use the default loader, but you can that is possible. But if you did not pre-process your validation data used yet, then maybe data loader, right? So data loader or default one. It depends on how you want to like execute your validation. So uh, based on your data, you can do that. Validation loader dot data, dataset dot data, so that it gives you a glimpse of the data, and that's the data looks like. This part is actually redundant. We already did the device. It is just redundant. You can remove this part and this line. Now you can see we want to see that true start, what is the true start position, true and the true end position, predicted start position, predicted end position. So those we will need for assessing the accuracy of the model. So here you can see this is a little bit more manual, so we run it in a manual fashion. We ask it to do the prediction. All right, so here is your like input IDs, attention mask, start position, end position, or those things. So you give these things and then call the model, right? And the model will give you the output. So you can do it manually, or you can do it through the evaluation function. Actually, Hugging Face has evaluation functionality as well, so you can use default one as well if you want. So in that case, you may need to change your dataset a little bit to fit the format. Okay, now you can see after the output, uh, we store that in the, so you predict here. After that, you can see what we do is, so I think this part is interesting. How do we predict the start and end position, right? So we have fixed length of the context, say 384 or something, right? So now this model will for the to give you the start position, it will generate a distribution for the whole all the token, for the all the tokens in the context. So what is the probability that first token is the start position, the second token is the start position, third token is the start position, right? So for all these tokens, it will give you a probability which one is the start position, right? So what I do is we take the max, whichever token has the maximum probability of being start position, we take that one through this argmax, right? So that is our start position, and then we store it in the predicted start position. Same for the end position. You get a probability distribution over all the tokens for your end position, and then you take the maximum probability as the end position, right? And then so that is like your predicted start and end position, and then you have the true start and end position that you get from your data, the batch data, because it is batch based. So we did the predicted and then the true ones for each batch. Okay, so you have all these things predicted and everything, right? And then this is the, like, this one is actually related to like finding the document location. That means it will give you the document ID so that you can map it back to your document for some purpose, maybe checking manually or publishing data and so on. So that's why it is here. It is not, it may not be important for you. So another thing is this functionality here. Because we are using tokenization, so if you have a small token, then maybe you get for one. So if you have a small word, say read, right? And then if you do the tokenization, you will get only one token. On the other hand, if you have a bigger token, a bigger word, for example, reading, so read will be considered as one token, and ing, that will be considered as another token. And now how do you know that this is coming from these two tokens coming from the same word? So they separate them through this double hash. So if you use double hash, then that will indicate that this is part of a bigger word. So using that thing, you can actually combine two tokens together to make one single word. So that's what we are doing here. You do that, and then so you do this post-processing for all of them, right? It's predicted and all the predicted answers. And after that, we convert all this prediction into a data frame, pandas data frame, to make it like look little bit, easy to investigate. So you have the document location. So as I said, this may not be needed for you. This is like which document we took the context. This is the question, the true answer. So where the true answer starts, and this is the predicted location of the answer. Sorry, this is true answer, the answer itself. This is just for sanity check. You may not need this one again. So this one is predicted answer, answer, what the answer was predicted, that we got through all this pre-processing. And here you have the true start position, true end position, predicted start position, and predicted end position. So all the information here, and then based on this one, you can apply many different evaluation technique to see what is the accuracy of your model. So here quickly we are visualizing the accuracy here. So this is the visualization for this one. And again, let me emphasize that we are using very small part of the data. Okay, so you can see the blue lines are like the total instances, and then the green ones is the how many instances were correctly answered, and the red means how many of them was wrongly answered, right? So this is the distribution for different questions. And you can see for some of the questions you don't have enough instances. For some of them you have enough instances, and then also the prediction accuracy varies for different questions, but overall they have like some trend. Usually usually the wrong answer is much less, but for some cases, for example, for this specific one, the wrong answer is more than the correct one, but for others it is the opposite. And then you define some functions to, as I said, you can find out what is the percentages of exact matching, half exact matching, any token match, or partial match, get F1 score, and so on, right? So you can do that, and if you call those things, you can get these things, right? So you said how many epochs you ran, and then what was the exact matching, percentage of exact matching, half matching, partial matching, the recall, precision, and F1 score. So you have all these things. Now, I think one question was maybe related to how to calculate the F1 score for your data, right? Usually, we have a document in the classification, and then we say whether it is a positive or negative, right? Or an instance positive or negative. But in this case, we don't have that kind of like a binary classification. Rather, we have different tokens. Now, how do we calculate the precision, recall, and F1 score? So how we do is actually similar idea, but instead of one document, you can consider each token as like one item in, right? So you try to see, for the precision, you try to see out of the predicted items or predicted tokens, how many of them are correct, right? So that is precision. For the recall, you want to see out of the predicted tokens, how many of them were coming from the true answer, right? So that gives you recall, and then if you take the harmonic mean, that will give you the F1 score. And so for one instance, like one question answer pair, you have one F1 score, and then you take average over all the instances, and then you get a average F1 score, right? So you can look into the code that actually then you can have a better idea of exactly how I am calculating. So you can do that. Yeah, and then also we did this distribution for each question, right? So for each question, you have the what is the F1 score, exact match, half match, and so on. And so for each question, you have the distribution. And then after all the training, we define a location where we want to store the model. So we save the pre-trained model. Uh, right? So later on you can load this model and then use it for prediction. So this part is based on the GR data. What is the time? So we started 4:30. Now it is more than, so it has been more than 1 hour. Do you want to take 5 minutes break? Then we will go for a squad data set, or you want to continue? Okay, let's have 5 minutes break and then we'll come back. Okay, hello everyone. Can you hear me? Okay, thank you. So let's start again. So this one was for the Dior dataset. Now, okay, I don't need this one actually. So now we will see how to train this model for a squad dataset. In the squad dataset, uh, you need to install these datasets, which is actually from Hugging Face. So if you install pip install datasets, that will give you collection of datasets from Hugging Face, and then from the datasets you call this function data load dataset. So and then from the load dataset you give the name of the dataset. So in this case, squad, and then it will load that specific data set. And also you can say um, how many instances you want to load. You can load the whole in the complete data set, like complete data set here, right? So you can load the complete, or you can load a specific percentage. For example, you can say to load 20% or something, right? Or we can say how many instances. So in this case, I said, okay, let us load 1,000 instances from the squad to train this model, right? And then after that, you can you take the squad data set and then split it into train and test. And then you need to say what percentage you want to use for testing, and you can say 20% in this specific case I am saying. So you have the squad data set with training and testing. You can say you can see in the training total there was 1,000. So in the training you have 80% data, so 800, and then in the testing you have 20% data, which is like 200 data points. Right? So you have this and then after loading, similar as before, you need to load a tokenizer. So in this case, the lightest one would be distill bird base uncased. I'm loading that one. And then this pre-processing is exactly same thing, nothing is changed. Exact same pre-processing we are going to apply here as well. And then you can see we apply this pre-processing to the data and use the default loader. Okay, now and same as before, we load the default pre-trained distilled but uncased one. You define all these things, epochs and other things, everything there, and then and you define your trainer. So in the trainer, you provide models and data sets together along with your tokenizer, and then you train the model. So number of training epochs, I said one, and then it will train only once, but you can set as many epochs you need. And then evaluation functions, similar as before. It takes all this information and then make prediction, and it stores that predicted information. And then you do the after prediction, you do the evaluation. So you first we convert it into data frame, and as data frame, and then same as before, define all the evaluation functions and do the evaluation, right? So that's all. So everything is similar, except that now instead of loading the data from a specific, like our custom data, we are simply loading it from the data set provided by Hugging Face, right? So that's pretty straightforward, nothing complicated. Do you have any questions so far? Okay, so if you don't have any questions, what I can do is we can run the model. So as I said, I will run it from CPU and GPU both. So that's why you can see I have two windows here. One is the one that I'm talking. This one is my CPU machine, and I have logged in from the GPU machine as well. So let me try to share my GPU machine. Mm, I think this is where we shared. It would be funny because it will share everything. Anyway, so mhm, okay, so you can see my code. Is the fonts okay, or I need to make it bigger? Font is okay. I'm not sure how to load dataset. Okay, I'll show you again how to load the dataset. So for the dataset, if you are using Hugging Face function, I will show you. So for example, this one, this is squad one, right? Yeah. So you don't need any link or anything. You just simply need to install this package, pip install datasets. So it is coming from Hugging Face, and then you can simply load your data from that package. So that is already by default it is available through this package. You will get the data. Okay, let's move here. So this is my CUDA package. But let me clear out all the output. Restart and clear output of all cells. Clear out. Okay. See, first one, we are going to check if we have the CUDA available or not. So I'm running that. Yeah, true. That means CUDA is available. And then we are taking the device. Which device is, if CUDA is available, we use CUDA. See, in the device, type is CUDA. So index is 0. Index is 0, that means yeah. So if index is 0, that means we are using the first CUDA. If you have multiple machine, you have say CUDA 0, 1, and 1, 2, and so on. I have only one, so it is just the 0. Index is 0. The first one I am going to use. Okay, then load this thing. Like from datasets, import load dataset. So if you import this package, that will give you the dataset, right? But in my case, I don't need this one for this file. We'll do it for the other file, so I don't need actually load this one. Rather, I will be reading data from my DOR dataset. So I load the DOR dataset. Well, I'm just using 50 points here, right, to like run it much faster than yeah. Uh, then you can see the data structure. You can see one example from the data. And this one is the tokenizer, distill part based tokenizer base case. So loaded, and then we define this functionality. So on this part, the pre-processing functionality. After that, we call this one to see the different columns and things there. It is just sanity checking, nothing important. Yeah, then we do the pre-processing through this mapping because we have only 50 instances. It is instant. It is done instantly, and then you use this default data loader, which is called default data collator. then load the pre-trained model. So there are some warning, right? So this is the name or the is deprecated and so on. So this is because of the version problem, right? Don't worry about this one. The version where I coded it was like older version, and now the version changed, and so you get a warning. That's okay. For now at least, and I'm testing from the latest version of PyTorch and PyTorch, Hugging Face, and also the Python. All the things that I'm running in their latest version, so it should run. Continuing with training method, so you define all these settings, and then you define your loader, trainer. Now, if you call trainer.train, it should start training. So we have only 15 instances, so it will be quick. The accuracy would not be very good, but yeah, the training will be very quick. Getting connection error, couldn't reach squad on the hub. SSL error. Did you check your internet connection if it is correct or not? Maybe. Oh, but I think you have the internet connection. Otherwise, how could you message me? Uh, hmm. Connection error, couldn't SSL error. Okay, so I will run the squad version of the module as well to see if I can find any problem. It should not be a problem. Let me check. Yeah, yeah. We'll run together to see if there is any problem. How about other people? You could connect to the for the squad data or not? For the squad port, let me try it on the CPU machine to see if the squad I can connect. So this is the squad version. Um, so obviously you can download the squad data online. That is possible. Let me see if we can get the squad data. We just try. So squad. So you can get it from this GitHub, right? So from GitHub you can download it, or you can download it from standard question answer, like I said, from Kaggle. So it is available on Kaggle as well. So yeah, you can get it from there as well if you want. Okay, so I'm trying to run the CUDA on my CPU machine to see if it is working or not. Question is, no, not this one. No, not this one. This one I need to run. Okay. So I tried from my CPU machine. It looks it is working on my side. Why the SSL error? For me, epoch runs still one only because we defined number of epochs equal to one. That's why. So you can change the number of epochs, right? Where is it? In the settings, you can tell the model how many epochs. So when you defined training arguments, so you can check there is something called training arguments, and there you said number of training epochs equal one. So instead of one, if you say 3 or 10 or something, that will run the model for that many times. So I can show you where it is. The setting C here. Number of epochs. Yeah, number of training epochs. So for the DUR dataset, I set it for 3 epochs, but for the squad dataset, the file that I shared with you, that one has training epoch defined as 1. That's why it is running only 1 epoch. So if you change that, that will fix the problem. So here, just if you change here, that should fix it. Okay, so let me see why you are getting this error. I'm not getting, I could not reproduce the error. So sometimes it is difficult to, check why you are getting the error if I can reproduce. Let me try. Yes, you can download it from Kaggle or GitHub. If you, okay, let me give you the link of the dataset, like Square dataset. Um, So you can download from Hugging Face, so from Kaggle. This is the link for Kaggle. So this is the link of the scope data at Hugging Face. You can try if you can check if you can get it from this link as well. It is good. So it looks like I have already managed to train 2 epochs. So the training is done for 3 books. You can see. Okay, now let's do the evaluation. So we set the model as in evaluation mode. So this is the model. This is the validation data. And this is how it looks like. And then do the validation batch wise. Okay, so validation is done, and then this is like some post processing. As I said, because we used only 50 instances, the accuracy would not be great. So this is what you're getting. And then for this one, you can estimate, and then you'll see lots of misclassification maybe. Let's do this one. This is the functionality. On those functions, you do that, and then you can see your recall. Not bad actually. F1 score is 70%. So not bad actually. The reason might be the portion I took is similar, very similar. That's why even with 15 instances, we got reasonably well accuracy. So you can say it for different questions. You can store your model if you want. Yeah, so everything is done, and then you can see that the whole model ran smoothly on my GPU machine without giving any problem. Now, so this one we ran for the DUR dataset, right? So what we can do is we can stop this and then run for the square dataset. So for the squad one, let me. So you load this package dataset loader. So here you're getting this error displaying widget. So this one is because that is, remember during the training you saw a progress bar that was going on. So that one, for this one, I think the JavaScript they use, maybe somehow I don't have the updated version of the JavaScript, something like that. But don't worry about this one. This error is actually just a visualization of that loading bar, so it doesn't matter. You can ignore this one, or maybe on your machine you may not get this problem. Okay, now you have the data set, right? So 1000 points, data points, 800 for training, 200 for testing, right? So you can see I could smoothly load the data without any SSL error or anything. So that's why I'm finding it difficult to understand why you are getting SSL error. Okay, so here we are loading the tokenizer, and then the pre-processing part, apply the pre-processing, and then get a loader, load the module. Okay, then you have the setting, and you can the setting and trainer, so done, and then you train your model. So here you can say the training is a little bit faster. The reason is the context of squad is smaller than the context of DOR. That's why it's a little bit faster. So here I trained it for one epoch. If I wanted to train it for more epoch, I had to change this one. So if you wanted 3 epochs, just set it to 3, right? So you can do that. And then after that, you do the evaluation because it is only one epoch. Obviously, accuracy would be terrible. I got some problem here. What is the problem? All tensor to be the cylinder, perform at least 2 devices, blah, 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 blah things. Okay. Mm. This one. Mm. English. Doing this one. Yeah. So, yeah. So it looks like there is some version change for this one. I fixed the doer part, but this one I didn't fix it, looks like. Um, mm, so my model is on GPU, valid loader. Maybe this part is not on GPU, maybe. Device CUDA. Mm, Let me see if I can fix it with device. Mhm. That is like one pain for using Python. They change the version and then you get in trouble with newer version. Mm. Ah, here you go. Yeah, here is the problem. So you need to send all the data to the device. I forgot to like fix this part. I fixed this one on the device part. Yeah, okay. Let me so I hope all of them are on GPU now. Yep. Okay. So now if we do this, yeah, now it is working. So it was like some of the tensor were not on the GPU. Okay, so you get the output. Now you define all these measurement techniques. Um, say you get this as output. Now you can see the F1 score is not good actually, only 38%. The reason you understand that we ran only for one epoch and also number of training instances were only 1000, not many. So, but you can see that you can run it without any hassle. Yeah. And some of you if you got the older version, right, and you're running on GPU, you can just simply uh, this three in this three or how many lines, 4 lines, there these two device part were commented. So if you uncomment this part, that should work. Get yeah. Okay, now I think yeah, it got fixed now. Okay, so we did this one, right? So it's similar to if you are successfully running it, I can quickly show you what happened yesterday, like why it was not running on GPU but on CPU. Like older GPU it was running, but it was not running for the like newer version of PyTorch. So so I will try to get to there. So this one, yeah, it was scan, and then this is hands-on, and then this is the master, and so this is GPU. If we clear this one out, So dataset from here is not working for. You need to check if your the dataset format in Hugging Face and the format you got from the Kaggle are same. Yeah, that needs to be checked. Maybe Kaggle is giving you in a different data format, so you may need to like change the format. Okay, so you started GAN model, 10 again. You can say let's try to run it on GPU today. When we loaded all these things, define the functionality, the settings. These are the file locations, everything. So you can see it is running, and then this is the settings. Nothing needed changing. Here we are deciding this device. The and then to device we sending the both the generator and discriminator on the GPU, and then you can print out and see. Then you need to move your binary cross entropy to the device, so we are doing that. So in the earlier version, if you move your binary cross entropy function to the device, and then any data you pass through this binary cross entropy, that would automatically go to the that GPU. But in the current like updated version, it looks like the process is not automatic. So that's why it was running on my old GPU machine perfectly, but it was not running your machine. So what you need is you need to see this data, the torch.full. So the label data that we created for the real and fake data. So this one, you need to add this part like to device. If you send your label to the device, as I said previously, it will go automatically to the GPU when you pass it to the cross entropy, but now they do not provide automatic movement. So that's why you need to specifically send this data or the label to the device. Okay, so now if you do that, this one is one, and the variable, see for the noise variable as well, you need to send it to CUDA. I think it was already on CUDA. If it is not, you can do that. So all the things were correct. Just if you fix this part, right, compared with yesterday. So if you do this, then it will fix your problem here. So after do this, you can say it will run now. See, it is now working correctly. So you just need to fix this line, right? So if you fix this line, like add this extra bit of code to device, then it will fix your code. That's it. Okay, so we have seen that our models are running on GPU perfectly. Let's see if it is running on CPU. Let's do that. So to do that, I will stop sharing the GPU machine, and then I will share the CPU machine. Share the CPU machine. Okay. Okay, for the CPU machine, which one we run first? I think we can run the squad data first because you don't have the Hugging Face data. But I checked actually it runs on Hugging Face runs on here as well without any problem. So for the squad one, restart and clear all cells. Which one is this version? Version 3. Okay. It should run it. So yeah, let's clear out all the things. Clear out football cells. Okay, so everything cleared now. Let's run it. This is the package of the data loader, and then you load the data. So you can see I could successfully load the data from CPU machine as well. And then let's load that. This is the tokenizer. So tokenizer loaded successfully. This is pre-processing functionality. And then do the pre-processing. Pre-processing done. So this is the same the bar that was showing the error. So on my CPU machine, that JavaScript is working, so I can see the bar. Data loader. Then we load the model. And then this is the trainer functionality, and then train it. See, it is successfully running. I didn't have any issue both on my CPU and GPU. And the GPU, my everything is latest one, like PyTorch, Python, and then also Hugging Face. I just recently installed everything, so it is working perfectly. So while it is being trained, do you have any questions? Okay, so turning down, do the evaluation. So yeah, now the accuracy is a little bit lower. But you can see it is perfectly running on both of my CPU and GPU without any issue. Let me try to find out why you are getting SSL issue. Connection error, SSL now. Mhm. Mhm. So one potential problem could for SSL connection could be, uh, let me check. Did you install your function from uh, the console, or you did it install from here? So see, if you run this part, sometimes you can get problem if you run from the cell. Rather than doing that, what you can do is you can run it from the command prompt. So Anaconda prompt, you run the Anaconda prompt as administrator. Okay, I need to get the administrator authentication. Yeah. Now, if you think run it as administrator, and on the prompt, run it as administrator. So you run it as administrator. If you do that, and then pip install dataset. Another thing is maybe you have pip3 instead of pip, right? So maybe pip3 install dataset. So if you do this, then this may fix the problem. Can you try, please? So you're saying you're still getting the same issue for the CUDA problem, but you saw that I tested it and it is working on my side, and that looks like weird. Yeah, I hate this thing about Python because of many versions and things. Sometimes it gets complicated why something is not working. Mm, what is this 1db.me? Dot me? I don't know. 1db server. Oh, it is coming from Google Colab. That- so you are running which model on Google Colab? The uh, question answer system for Squad? Hmm, interesting. I didn't check with Google Colab though, but it should run on Google Colab as well. It is saying runtime run name is currently set to single address. And if this is not introduced, blah, 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 blah. So one thing is external site. The host presenter would like. Mm, it looks like it is related to some sort of authentication issue. Let me see if I can. So this is authentication error, and it is related to the dataset that. Uh, mm. For Sunita, so you used pip install datasets, right? And then after that, you're getting the problem. Mm. So in any case, are you using your office computer instead of like home computer? Uh, so it might be in your office you have firewall or something that is preventing to access this website for this data set, right? The server of the data set. That might be the reason. That's why you're getting this SSL problem or these kind of things. Uh, that could be potentially could be the reason. But on home data is not downloaded, so using cloud. So what do you mean by data is not downloaded? You're getting error when you're running the code from home computer? Interesting. Um, I can try to match some of the things. Let me see. So we can. I'm trying to investigate. So one option could be to write it. Um, to everyone. Okay. So I'm using Python version of 3.12.3, right? So I'm just trying to see if we are using similar thing. And then PyTorch, I need to know the PyTorch version, right? So I'm checking everything. Mhm. Mhm. And then let me check the version. And then my Torch version. Mm, So this is my PyTorch version, 2.5.1 CUDA 118. So this is PyTorch. Let me see the Hugging Face version, right? Uh, Check the transformer version. So my transformer version is 4.48.0. So these are the like three main things. Other than that, I'm using everything default. I didn't use anything different. So if you are using similar environment, it should work, I think. Okay, so I have mentioned what is the Python version, PyTorch version, and Transformer version. I think there are some local assistants that where you can get some help, additional help to figure out why you are getting this security issue like SSL problem or like problem with getting the data set, right? So other than that, it looks like so what we did is we tried to understand how to use language model and GAN-based model to do the information extraction. In the hands-on part, we saw how to run it, explain all the codes for the information extraction. We demonstrated running the code both on GPU machine and CPU machine, and at least in my end, for both cases, it was working smoothly without any problem. And still, if you are getting problems, and it is possible because some related to some versions or security issues, sometimes you can get problem. So I think you can get local assistance for that. So other than that, we can wrap up today. You will have another modules next week, and the two modules yesterday and today's modules. There will be quiz on Saturday, and then there will be module on Saturday and Sunday, right? Mm, so thank you all for attending this module. Yeah. See you in future. Thank you very much.